Today, we are diving deep, and I mean deep, inside the atom to get to know the most powerful force in the entire universe. This is the force that literally holds our reality together. We are talking about quantum chromodynamics.
Just think about it for a second. You've got the nucleus of an atom, right? It is packed, just jam-packed with positively charged protons. Now, everything we know about electricity says these things should be repelling each other with an incredible force. They should just fly apart, but they don't. So, what's going on? What is this cosmic superglue?
Well, the answer is found in one of the most successful and honestly one of the weirdest theories in all of physics. So let's talk about the universe's strongest glue.
That glue is called the strong interaction, and the theory that describes it so beautifully is called quantum chromodynamics, or what we'll be calling QCD. It's a cornerstone of what's known as the standard model of particle physics, and believe me, it governs the subatomic world with a set of rules that are, well, they're pretty out there.
Okay, so to really understand QCD, you have to meet the main characters in this subatomic drama. These are the fundamental particles that make up pretty much all the stuff you see around you.
First up, you've got quarks. These are the real building blocks of things like protons and neutrons. Now, they come in 6 different types, which physicists, in a moment of whimsy, decided to call flavors. You've got up, down, charm, strange, and so on. But they also have this other property, and this is the one that's the key to the whole theory.
And the things binding them together, those are the gluons. And yeah, the name says it all. They literally glue quarks together to make bigger particles. But here's the kicker. And this is what makes the strong force so different from, say, electromagnetism. You see, photons carry the electromagnetic force, but they don't have an electric charge themselves. Gluons, on the other hand, are absolutely dripping with the very charge of the force they carry. This means they interact with each other, and that changes everything. So what is this charge? Physicists call it color charge. Quarks can be red, green, or blue, and gluons carry combinations of these colors. And I have to be crystal clear about this. This has absolutely nothing to do with the actual colors we see with our eyes. It's just a clever, kind of poetic naming system for a whole new kind of quantum charge. Now, this world of color charge, it doesn't play by the rules we're used to. It operates under 2 principles that are unlike anything in our everyday lives. They're bizarre, they're powerful, and they are completely fundamental to how our universe works.
So rule number 1 is color confinement. What this means is you can never, ever find a quark or a gluon all by itself, just hanging out. You see, unlike gravity or electromagnetism, the strong force doesn't get weaker with distance. It just stays constant. The best analogy is a cosmic rubber band. The more you try to pull 2 quarks apart, the more energy gets stored in that band, until, bang! All that energy creates a brand new pair of quarks right out of the vacuum. You never break the band, you just make more particles. You can't win.
And if that wasn't weird enough for you, rule number 2 is asymptotic freedom. This is a total reversal of how we think forces should work. When quarks are super close together, crammed inside a proton, the force between them is incredibly weak. They just kind of float around almost freely. But the moment they start to move apart, that force becomes overwhelmingly strong, yanking them back. Weak when they're close, strong when they're far. It's this fundamental, mind-bending duality. You can imagine that these ideas sounded pretty wild at the time. So wild, in fact, that even one of the fathers of the quark model, Marie Gell-Mann, was skeptical at first. He thought, maybe quarks are just a useful mathematical trick, not actual physical things. I mean, if you can never see one on its own, how can you say it's really there? Well, it turns out they are very real. The theory of QCD didn't just tidy up some old puzzles, it made a series of absolutely stunning predictions that were later confirmed by experiments, turning it from a weird idea into a pillar of modern science. So let's take a look at some of QCD's greatest hits. Getting here was a journey, for sure. It really kicked off back in the 60s with the quark model, which was just trying to bring some order to the particle zoo of new particles being discovered. But the massive breakthrough, the real game changer, came in 1973 with the discovery of asymptotic freedom. That's what finally made it a viable theory. After that, the floodgates opened. Evidence just poured in, from finding new kinds of quarks to getting the first direct glimpse of gluons in action. And the successes were just spectacular. QCD explained exactly what scientists were seeing when they fired electrons deep inside of protons. It predicted that when you smash particles together at super high energies, you wouldn't see loose quarks and gluons, but these narrow sprays of other particles called jets. And that's exactly what we found. It even predicted that at insane temperatures, like right after the Big Bang, a whole new state of matter could exist, a quark-gluon plasma. And guess what? We've actually made it in our colliders. Honestly, that one idea, asymptotic freedom, was the key that unlocked the whole thing. It's what transformed QCD from a kind of speculative model into a precise predictive scientific theory. It was a feat so important, so fundamental, that it earned its discoverers the Nobel Prize in Physics in 2004.
But here's the thing. For all of its incredible successes, QCD is not a finished story, not by a long shot. In fact, some of its biggest mysteries are what make it one of the most exciting fields in physics today. There are still some really deep puzzles left to solve. All right, so here's the first big one. We know color confinement happens. Every single experiment confirms it. But no one, and I mean no one, has been able to produce a complete, totally rigorous mathematical proof that starts with the basic equations of QCD and ends with confinement. It is such a hard and important problem that it's actually one of these 7 Millennium Prize problems in mathematics. There's a $1 million prize waiting for whoever solves it.
And here's another puzzle, one that's a little closer to home, the proton spin. You'd think it's simple, right? You just add up the intrinsic spin of the 3 quarks inside, and that's your answer. But it's not. That only gives you about a third of the proton's actual spin. So where's the rest of it coming from? Is it the spin of the gluons? Is it the quarks and gluons whipping around inside? We're still trying to figure out the exact recipe.
And then we have maybe the most exotic question of all. If gluons can interact with each other, could they clump together and form a particle made of pure force? A glue ball? The theory says, yeah, they should exist. But finding one has turned into this epic cosmic scavenger hunt. They'd be incredibly unstable and could mix with other particles, which makes them almost impossible to spot.
So answering these huge questions, it's going to require pushing the absolute boundaries of both our experiments and our theories. So what does the future hold for our understanding of the strong force?
We're basically attacking these puzzles from all fronts. We're building new colliders designed to give us the first ever 3D pictures of the inside of a proton. Our supercomputers are running these massive simulations to calculate particle properties from the ground up. And looking ahead, quantum computers might one day be powerful enough to simulate this crazy theory directly. And all of this work, it isn't just about tiny particles. It's absolutely essential if we ever want to understand extreme cosmic objects like neutron stars.
So you see, quantum chromodynamics is far from a closed book. It's a foundational, dynamic, and frankly, a really challenging field of physics. It describes the glue that holds our entire universe together, but it also holds these deep, profound mysteries that we are just beginning to get a handle on. The real question isn't just what we know, but what amazing new things we'll find when we finally turn the page and get to read the next chapter.